Good morning, everyone. My name is Hangfei Dong from Hanyang University in Korea, and my advisor is Professor Simon Song. In this presentation, I'm going to talk about analysis of flow behavior in a refrigerator machine room using magnetic resonance velocimetry. So MRV is an innovative and exotic flow visualization technique. I hope you will find this talk informative. First, let's see the background of our research. Everyone loves a refrigerator that has high energy efficiency and doesn't make much noise, right? So to this end, engineers need a comprehensive understanding of the internal flow distribution and decay characteristics when design a refrigerator machine room. As you can see in this picture, well, there are some 2D model-based experiments or safety studies available. We lack sufficient experimental benchmark data based on 3D velocity and turbulent kinetic energy. As you know, optical-based techniques such as PIV cannot visualize flow with an opaque and complex flow environment, such as the machine room's interior. So this is where MRV comes into play. So in this slide, I will give you a brief introduction to MRV. MRV is a flow visualization technique that uses a conventional MRI scanner. Unlike other techniques, it measures in a 3D region and is a non-invasive flow visualization technique, meaning it doesn't require any tracing particles. And because MRV uses magnetic field signals for measurement, it's suitable for complex and opaque flow environment, and MRV allowing flow measurements to be completed in a short time. And the highest spatial resolution we have conducted is 0.2 millimeter. Furthermore, MRV can measure a wide range of characteristics, including velocity, decay, temperature, concentration, and Reynolds stress tensor. Therefore, the objective of this research is to visualize the mean velocity and decay in a refrigerator machine room by MRV and provide three-dimensional experimental benchmark data for improving the design of the machine room. First, we aim to measure and analyze the characteristics of the three-dimensional and three-coordinate mean velocity and decay of a flow in a 3D printed model of a refrigerator machine room, and we wanted to propose an improved geometry with higher flow rate and more uniform flow distribution through the heat exchanger and the lower decay. Next, I will briefly explain our experimental setup. As you can see in this picture, we have a closed loop circuit, including a pump, an electromagnetic flow meter, a refrigerated and heating circulator, and some data acquisition instruments. And for this experiment, we used a phantom, which is a reservoir with a half-scale machine room model placed inside the MRI scanner. So to suppress any disturbance caused by the incoming flow to the machine room model, we inserted a flow conditioner to the right side of the reservoir. The flow enters from the right inlet, passes through the expander, flow conditioner, machine room model, contraction, and finally exits at the left outlet. As a working fluid, we use a copper sulfate aqueous solution is used instead of air. The fluid was set to 13.2 RPM to make a Reynolds similarity. Next, I would like to explain the LG mass-produced reference model and improved model proposed through our research. First, we change the direction of the set inlet and outlet to a horizontal direction and increase their area by 60%. Next, there was a guide when we look down from the top of the rear panel and we remove it. And next, we change the two-stage inlet to a single one-stage. And next, we plug the inlet in the bottom panel. For the sixth, we move the refrigerant pipes to a location with less flow interference. And finally, we relocated the flow blocking pillar. The reason for structural modification will be explained in the research result. So from now on, I will talk about the result of the flow visualization. Firstly, I will show you the result of three-dimensional velocity measurements. So as you can see in this video, the flow enters from the red inlet, passes through the condenser, fan, compressor, and finally exits at the left outlet. So okay. And the next is the mean velocity cross-section result of the reference model taken along the y-axis. The spatial resolution is 0.5 millimeter and the number of signal average is 4. So the arrow indicates the in-plane velocity, while the contour indicates the out-of-plane velocity. The white area represents a part with low signal intensity, which is the area occupied by the structure. So let's see this video. We can see that the flow enters from the inlet and passes through the refrigerant pipes condenser, and this is the fan system. And next, the flow will passing through the compressor, and finally access from the rear outlet, bottom outlet, and and the left outlet. Okay, the next result I will show you is a video of the TKE for the reference model taken along the y-axis. So unlike the mean velocity result, the spatial resolution is 1 millimeter and the number of signal average is 30. So through this video, we can confirm areas where the flow is non-uniform and the TKE is high. Okay. So the next is the 3D streamlines result and the comparison of flow rate through the heat exchanger along y-axis. On the left side, we can see that the 3D streamlines for both the reference model and the improved model. The red box indicates the heat exchanger zoo, while the total flow rate passing through the machine room model's interior is constant. The flow rate passing through the heat exchanger zoo differs for each slices along y-axis. So to quantitatively investigate the flow rate through the heat exchanger, we define the ratio of effective flow rate. This is calculated as the flow rate through the heat exchanger zoo divided by the total flow rate. So as you can see in this graph, it will confirm that the flow rate through the heat exchanger of improved model was increased by 17% compared to the reference model. And next is the TK mapping result. The reference model, especially at the downstream of the two-stage inlet and the left side of the condenser, shows a relatively high TK. In the improved model, the areas with high TK value were reduced a lot. And the right side provides a quantitative comparison of the number of voxels in each given range of TKE for both models, as well as the reduction ratio in the number of voxels. So from this table, we can see that the number of voxels with a higher TKE range were reduced greater than those with a lower TKE. So as you know, a turbulent flow generates vortex that create pressure fluctuations and sound waves, resulting in flow-induced noise. Therefore, this probably leading to a reduced turbulence-induced noise. And from now on, I will discuss the changes in flow characteristics resulting from our structural modification. Let's start by looking at this plan. In the reference model, the inlet angle is direct upward, leading to a non-uniform flow towards the heat exchanger, and there is a large-scale secondary flow motion, resulting in an energy loss. The improved model with horizontal flow direction at the inlet and 60% increase in area shows a more uniform flow distribution and a higher speed. And next, we will discuss the effect of removing the guidance and location change of the flow blocking pillar. As you can see, these two modifications had a significant impact on the flow entering from the inlet, leading to the elimination of a bypass flow and a rapid flow band between the condenser and the rear panel. Therefore, the improved model without the guidance and location change of flow blocking pillar, you can see that more flow is directed into the condenser and the lower TK distribution. Okay. And next is the effect of two-stage and one-stage inlet. In the position of this plan, reference model shows a very high TK due to the structure of the two-stage inlet. By changing the two-stage to a single one-stage, we can see that the improved model shows a significant reduction in TKE distribution. And next is the effect of the refrigerant pipe's location. In the reference model, since the refrigerant pipe is located downstream of the inlet, the TKE value is inevitably high. By relocating the refrigerant pipes with less flow interference, we can see a reduction in TKE distribution. And here is the result of 2D flow profiles located before entering the condenser for both models. The flow uniformity index, a dimensionless parameter used to quantify the uniformity of flow distribution, is defined as follows. A flow uniformity index closer to 1 indicates a highly uniform flow distribution. So from this result, it was confirmed that the improved model, our proposed structural modification enhanced the flow uniformity. So in this study, we successfully visualized the three-dimensional mean velocity and TKE inside the refrigerator machine room by MRV. In the improved model, we proposed the mean flow rate through the heat exchanger is increased by 17%, leading to a higher thermal efficiency, and the region of a high TK value were reduced by more than 80%, probably leading to a reduced turbulence-induced noise. And due to time constraints for this talk, many topics were not covered, such as the process of Reynolds similarity, validation of MRV flow conditions, and the measurement uncertainty of velocity. So if you are interested in these topics, you can refer to this paper for more information. And finally, I would like to introduce several other applications of MRV in engineering flow. First, in refrigerators, the evaporator and the central fuel fan are key components related to energy efficiency and noise. In the evaporator, the refrigerant transitions from liquid to a gas state, absorbing heat from the surrounding air and cooling it. Then the central fuel fan circulates the cold air within the freezer compartment, while these two components enable the maintenance of low temperature in the freezer, so they are primary sources of heat and noise generation. Therefore, by applying MRV to the refrigerator freezer, we can understand the flow characteristic inside the freezer and could lead to more energy efficient and low noise design. And next, we applied MRV to study the flow inside the muffler of a reciprocating compressor. As you know, a muffler is used to reduce noise. However, when refrigerant passes through the muffler, it experiences additional pressure drop and heat exchange, which can affect the overall performance of a compressor. Therefore, understanding the flow characteristics inside the compressor is very important when designing a compressor, and MRV can do it. And this is the end of my presentation. Thank you for listening.